All right? So this is just an energy balance. And it came from making a control volume very tiny. Ying spent a whole of a Friday like 3 weeks ago doing this. Okay, so right here I am assuming something. What am I assuming? Constant K, I like that. And thank you for saying constant K and not constant alpha, because the truth is constant K, what we assumed. Right? We're assuming constant K, right? And if you go back to this Friday 3 weeks ago, you're going to see why this is so. We're assuming something else in addition to a constant K. We're assuming that this is isotropic. Because if it was not isotropic, even if K was constant in space, this would be a matrix. And the equation would be a lot more complicated. But if we say it's constant K isotropic, we did that. Now, just because I'm in a generous mood today, I'm going to keep knocking things out. Let's say we have no heat generation, just for now. And let's say, okay, given the title of what I'm discussing today, what else should I do? Right? This goes, right? Because it's steady state, right? I'm going to write it down, steady state. This one I said that goes because I just don't like it. It's my party. It's out. Okay, so, okay, here's the beauty of this. What are we left with? Now we're left with this. Isn't that awesome? For those of you who think this is now a trivial equation, let me wake you up. It's not trivial at all. Actually, it's a very general equation in engineering. This is an equation you would use for heat transfer, for fluid mechanics, for diffusion, for electromagnetics. I mean, this equation is pretty much universal, right? Now, this equation that looks easy, right? What should I write now? What is it missing to come alive? Because this equation looks stupid as it is. What? Well, this okay, let's write it down. In 3D, this is, right, in 2D, this one is the one we did for the plane wall. What are we missing here? The boundary conditions. That's the killer. That's the killer. This innocent-looking thingy, this is going to kill you, because that depends on what the geometry is. Is that a square? Is it a cylinder? Is it a sphere? Is it a Mickey Mouse? I don't know. Like the water is a constant temperature at the surface. Is constant heat flux. Is the boundary conditions of the third kind, right? Don't be fooled by the looks, right? But the good news is that we have ways to tackle it. Location of points at the same temperature. All right. In 2D, what do the isotherms look like? What are those? What geometric element are those? Those are lines. These are lines in 2D. We're going to do some examples. What is an isotherm in 3D? It's a surface. And this is very important because if you were looking here you have isotherms. Actually, the ones on the left, we did them in the lab, right? That's during welding. That is with a thermal camera. We have a thermal camera that is $125,000. That's not the drywall inspection thermal camera, right? And what you see here, the isotherms here, right? would be the lines of the same color, each line of the same color, right? But the funny thing is you don't see under the surface, but under the surface you also have isotherms, right? It's because it's a surface. Adiabats. This is probably something you have not heard before. Seldom used, but the book talks about them, and I think it makes sense to know them. You know what these are? These are the lines of flow of heat. Now, you can prove with very simple math, but we're not going to do it. You can prove that isotherms and adiabats are perpendicular. So they cross at 90 degrees. And when in a 3D problem in which the isotherm is a surface, the adiabat is a line that pokes that surface right at 90 degrees. So let's have a plane wall. So here we have TS1, and this is TS2. So is TS1 and TS2 isotherms, adiabats, something else? Thank you. Well, you said probably, but for sure they are isotherms, because we're saying every point on this surface is the same temperature, same as this other point here, right? What does an isotherm inside this wall look like? It's just parallel, right? And another isotherm would be here, right? If I ask you, what is the temperature of this isotherm? Would you know it? By now you do, because it's a plane wall. And actually, we said that the gradient between these two is a straight line, right? So it's just a triangle. You just work with triangles. You can do it in so many ways. But here's how this class is taking you beyond the just plain intuition, right? We understand isotherms, and I actually think you don't need to study engineering to understand this issue of isotherms in the plane wall. But now you can calculate them, and it's trivial. But we're putting the concepts together. All right, that was our isotherms. What do the adiabats look like in this case? The lines of flow of heat. Right. So the adiabats would, assuming that TS1 is bigger than TS2, right? And here we have, right? What is the flow of heat in an isotherm? If I pick an isotherm, whether it's a surface or a line, on that surface or on that line, what is the flow of heat? Zero. Who said that? Thank you. It is zero. Has to be zero if everything is at the same temperature, right? How are you going to transport heat on the isotherm, right? So heat doesn't move in that way, and it moves all the way here. When we calculate that in a plane wall, the heat goes according to the whole area. It's because we're assuming the whole area is like always the adiabats move straight across them, right? So in that case, if the heat is moving in this direction and it's not moving in the direction of the isotherms, what it means is that here we're insulating them. Not a trivial concept. Do you follow me? If the heat flows, say, I am heat and I'm flowing in this direction, parallel here to the board, right? How much heat, how much of me is going across the board? Right? Again, I am heat going that way. How much is going across the board? It's zero, right? If I were like to come in a slant angle, then I would be banging my head, but I'm not, right? So if heat is not crossing a line, means that line is adiabatic. That's why it's called adiabats. And the reason I'm bringing up these adiabats is because those are the lines that correspond to insulated surfaces. So, for example, if you have an insulated surface, and again, look at this. This is just, we're doing zero math. We're doing zero math, but we're getting important concepts here. Let's say, another example. Insulated surface. All right. Tell me what the isotherms look like near this insulated surface. What do the isotherms look like? That's what you're saying, right? I don't know how they go far from the surface. Is everybody on board of why I made them this way? I made them this way because, look at this, 90 without the dot. Right? Is because if I have an insulated surface, that is an adiabat. And isotherms are perpendicular to adiabats. How about that? Isn't that pretty cool? You know this. Now imagine the surface is not adiabatic. Yeah, and it's not isothermal either. All right, here I have my surface. Right? I don't know what symbol to do for a non-insulated one. If this is my surface, and I have this field here of temperatures on top, what would the isotherms look like against that wall if it is neither isothermal or adiabatic? If it is adiabatic, they're perpendicular, right? We all agreed on this. If it is isothermal, now they're all parallel. Right? You know that your head, every time as I went through each of these steps, now I'm putting the steps together and it's like, oh my God, right? So in this case, we would have something like this. Right? Isn't that neat? You start figuring things out. You start to understand. Now, if you see isotherms that are not perpendicular and not parallel, that means there is heat flow through that wall. Yes? Okay. I will not write it here, but this angle has a lot of meaning because this angle here, imagine this is hot and cold here, right? This is the gradient here, right? And you can decompose the gradient as the heat that goes through the wall and the heat that goes parallel to the wall, right? And we didn't do any math. But you can say so much. You can spot many mistakes immediately. Mistakes that appear when students give their doctoral exams. For a cylinder, right, yeeks. Here we have TS1, and here we have TS2. What do the isotherms look like? They are cylindrical, right? The isotherms here are other cylinders going inside. Okay? What do the adiabats look like? Yeah, like spokes of a wheel, right? Radiating from the center like rays of sun, right? So, something that there are many people who they engage heat transfer from the point of view of numerical analysis and finite elements and whatnot. And it gives you these amazing colorful plots, and you feel so happy with yourself, and you want to hang them on the wall. But seldom there is an intuitive feeling, an intuitive grasp of what's going on. And above all things, I hope to help you develop this intuition. Eventually, you'll put it in the form of math. But intuition is the most important thing. It's like playing the blues, comes from the heart. That you learn the scales later.